Swayam Prabha. Digital India. Educated India.
So today's class we are going to look at simulation and animation of dynamics using MATLAB for mainly ordinary differential equations. How do you simulate ordinary differential equations and do their animation? Okay, very interesting way we can do very nice stuff using MATLAB function called ODE45. Okay. So before going through this, so we need some representation of a system for the simulation. But I would say before going through this part, you may look at actually the MATLAB help on ODE function. Okay, so for that maybe I'll show you first what it produces, and then maybe we can come back. Okay, so we'll go to this window and look at, see, this is a command I have issued here, help ODE45, and it gives all this kind of non-stiff differential equation, and so you just kind of read through all these things, and then maybe we can come back, and then whatever I'm talking here will make much better sense to you. Okay, so let's come back here. So you can read through this help. Okay, you can pause and read through, or you can have your own MATLAB software and then go through. Okay, so let's come back now to the simulation here or PPT here. Okay, now so for this you can see now that this MATLAB ODE function will be able to solve the ordinary differential equations which are represented in the specific form. This form is like this, where this x here is a vector function, and its only first derivative is here, is equal to f of xt, and f is some general nonlinear function of x and t. Okay, so and again this is a function of x as a state coming up here. Okay, so whatever state it is a function of, it is giving the derivative of the state up here. Okay, that is what is the meaning of this equation, and this equation is what we need to convert all our systems to this form of equations, and we'll see how we do that by an example. So if you have a system of the kind simple spring mass damper system, so mx double dot, cx dot, and kx are three terms is equal to 0. So this is not in this form, right? Because this has two derivatives up here. So we need to kind of convert to this form. We need to do something. So what do we do? Think about this. What can be done to get it into this form? Pause for a while here and see what comes to your mind, and then we can see the next. Okay, what we can do is we define this, introduce this additional states into the system. Since this is double derivative here, and I want only single derivative up here, but many different kind of variables can be possible. So I define these additional variables here, x1 and x2 are the two states. They are defined such that when x1 is equal to x and x2 is equal to x dot. So when I take derivative x1 dot, it will be equal to x dot here, and x2 dot will be equal to x double dot. Okay, and that's how I can get this state derivative here. Now I want to represent the state derivative in this form here. Okay, so how do I represent that? When I take x dot, you can see that x1 dot is equal to x dot. Now I cannot use x variable because I have to convert. I have already transformed the system into these two additional variables. So I will use now x dot. I know is to be defined as x2. So x1 dot is equal to x2 will form my first equation, and then x2 dot is equal to, again this expression comes from this equation, and here again I cannot use x, I have to substitute them with either x1 or x2, which is done here. Okay, so this is how I can get this function defined. So this is my f1 here in this equation, and this is my f2 in this equation, and this function is now ready for coding, for doing the ODE solving. Okay, so now we'll see this for applied for the spring pendulum kind of a system example. Okay, so again the ordinary differential equations we simulate which will come for this spring pendulum system. I'll show you what these equations are in a minute, but just to give the settings, like this is pendulum is considered as rigid body, and it has its own inertia of rotation, okay, about the z-axis, and radius of gyration, okay, or mass moment of inertia, it will be coming from the radius of gyration, is given as r. So mass moment of inertia is mr square for this bob around CG axis passing through CG and z-axis, okay, perpendicular to this page. Okay, then the spring is considered as a stiffness, nonlinear stiffness. Why? Because typically, for actual example or actual practical case, this can be a rubber like a string, and rubber, as it stretches, its stiffness starts increasing. So it has some kind of a cubic nonlinearity which will be increasing the stiffness as the stretching happens. Okay, so that is also incorporated in the equations. Okay, so considering this nonlinear spring, and important other thing is this L is unstretched length of this spring. Okay, this unstretched length is L, and then beyond that the stretch X is deformation that happens. With this kind of a setting, these are the equations of the system that are obtained. Okay, so now you can see there are two equations which are second order equations. So mx double dot, equation in the direction of this L, it moves up and down like that here, and then there is a equation in the direction of theta. Okay, so theta double dot direction. Okay, theta is another kind of degree of freedom. So theta is a degree of freedom, x is another degree of freedom, and you have this 2 degrees of freedom system with 2 differential equations governing that dynamics. Now the question is, how do we convert them into our form? Okay, which you remember the form is x dot is equal to f of x and t. So again, now we need to define a new vector of 4 variables. So what is a variable of your choice? Here, since we have these 2 degrees of freedom, x and theta, naturally we use them and their derivatives in defining this vector. Okay, in the similar way as we did for the simple spring mass system. Okay, so theta double dot, theta dot we say as y2 variable, theta as y1 variable, then y3 is x, y4 is x dot. And now if we see the derivative of this state, it is having this y1 dot, y2 dot, y3 dot, y4 dot. Now y1 dot by definition is theta dot here, and theta dot by definition is y2, so this becomes y2. Like that, the y2 dot by definition becomes theta double dot, and y3 dot becomes y4, and y4 dot becomes x double dot. Now this theta double dot and x double dot can be obtained from these previous equations of dynamics that you saw here. These equations of dynamics, this will give you the x double dot, and this equation will give you theta double dot. Okay, so how do you obtain them? By using moving all these terms on the other side and then dividing that by m, you will get x double dot. Moving all these terms on the other side and dividing them by this term, you will get theta double dot. Okay, and then we substitute them here, and our function f1, f2, f3, f4 is ready for simulation in MATLAB. Now how do you code them? Okay, so this is first function. First, you have to code this function. And how to use this function in the OD45 command is what we'll see actually in the program. Okay, so clear for so now how do we develop this code? So I would suggest, like, no, you don't see this code first, you just go ahead and, like, no, write your own way this code, assuming that this state is given, this vector is given. So if there is a function f we have to write, for which the arguments are t and y. So you are given y as a vector quantity. That's we have to keep in mind that, okay, it is coming in argument as a vector quantity, and then you know this y1, y2, y3, y4, and from this you need to produce, like, you know, their derivatives, y1 dot, y2 dot, y3 dot, y2, y4 dot, by using this part and these equations as we explained. Okay, so this is how you will write a code, and once you write a code, then so pause it for now here, write your own code, and then, like, you know, you come back, then you'll find, like, you know, if you have made any mistakes or your understanding is missing somewhere, that will open up, like, you know, that becomes like a firm understanding within you. So don't, like, you know, go to the next part unless you have written the code yourself. Okay, now we'll go to the next slide and see this code. Okay, so here now I'm defining all these terms in some kind of a fashion, whatever, some kind of a physical quantities, and then writing, like, so I'm assuming, like, you know, that for this function y is coming as an argument in vector form. So y1, y2, y3, y4 will be my 4 states, y of 1, y of 2, y of 3, and y of 4, like that. And then, so this, like, you know, is how it is used here. And then I need to produce a derivative. So dy are like derivatives of these states. So dy1 is equal to y2, dy3 is equal to y4, and dy2 is as I explained from this formula. Now you, wherever there is a theta, you substitute corresponding y, and then you can kind of get your equation coded. Okay, so this is the equation for theta, and this is a theta double dot, and this is the equation for x double dot. Okay, this is how, like, you know, you write this code, and this function ends here. Once this function is written, now let us see how we can go ahead and simulate it. Okay, so let's switch back to MATLAB window. Now here we have this function written in MATLAB. I'll show you already written function here. Okay, so this code gives you the function written as we have seen in the slide. Okay, and now you can see all these arguments and functions written properly, and you can write whatever comments and things you want to write. Okay, how do you use this function? Now once you write this function, then, like, save it, you use it in the ODE command like this. So for ODE command, you need to define this initial conditions. The initial conditions in this case are taken theta is equal to minus pi by 3, and x, some deformation is given to the x to begin with, some spring is deformed by some amount, and then time is defined for which you want to produce this output. And then you can see that this time and initial conditions are going as other arguments to this ODE45 function along with the function that you have written. So this will output the state evolution, okay, y in the same order, y is in the same order as you have coded in this function. It will be output here, and then time will come as a, so this is like a time trajectory of all the states that is coming up here. And then you have the animation creation up here. So you create some figure, and in that figure you draw these lines, and this bob of the pendulum is drawn as a simple point or circle with the size of the circle big enough for us to visualize it nicely. Okay, so that is how, like, you know, these things are plotted, and you plot it, delete the plot, and again replot it for, like, you know, next update of the time. Like that you can do in a loop and, like, you know, create this animation. There are many different other ways also of creating animation. You may find some more links on the YouTube or on the MATLAB website, and you can create different kind of ways when animations can be created. So if you run this file now, you will find it produces this nice animation of a pendulum. Okay, So you can see that this pendulum is oscillating, and at the same time it is having the vertical or the radial direction stretching and unstretching that is happening for the spring. Okay, so of course here we are not modeling it as a string. So for example, like if the compressive force becomes too high, like the string cannot get compressed. Okay, but spring can get compressed. So if it is a rubber band like a string, then it will just simply not get compressed further. But we are not capturing that part here. So if the spring force is always positive, like or there is some stretching in the spring always there, then you'll have no issue. Like this will be a realistic kind of a simulation happening in the system. Okay, then I would like to kind of give a little bit more attention to this other. Let me close this window. Part of the files. This latex.fig is a file that is written for setting the global variables of a figure that can be controlled in a nice way, so as to create figures which are good for the latex document or their manuscript or papers that you write. No, so this file will be of immense help if you run this file, then use figure command in MATLAB to plot any, or plot command in MATLAB to plot any figures. Then all the settings will be done nicely for, say, a latex kind of a document. Okay, and you have other file where ppt_fig kind of a name is given. This file, when you run and plot your any of the figures, then this will create a setting which is good for PowerPoint presentations. Okay, so you may use these files in a way for your future activities as well. This is very interesting, nice way to kind of create environments for you, and you don't have to worry about somebody pointing that, okay, oh, your pics are looking so small, I cannot see them, and those kind of things will not come into picture when you start presenting with these use of these files. Okay, so we'll come back to our presentation now. We are here. So one more case we need to discuss here before we close is the case of systems where you have the coupled dynamics coming up here. Coupled in the sense that it has a double derivatives coupled. Okay, so you have this d11 q1 double dot and d12 q2 double dot coming in the same equation. Okay, so far we had systems where only one double derivative was there in one equation. So there are now these two different quantities double derivatives are coming. How do you handle such case? Okay, so how do you basically now represent the system in the form that is required for the ODE solver to have? You remember that form? The vector x dot is equal to f of x and t. Okay, so we want to kind of get the system in that form. These other quantities will not bother us because they are all as coming as q dots only. Okay, there is no any double dot terms anymore here. Okay, so how do you handle such case? How do you do? What do you do? How do you transform? Think about that. Okay, and then you go to the next slide. Pause here and then go to the next slide. Okay, now here what we do here is basically convert this system into matrix form. Okay, this is like a matrix vector form. This is a matrix here, this is a matrix here. The G is a vector of this dV by dou V by dou Q1 and dou V by dou Q2. Okay, so that GV forms a vector, tau forms a vector of tau1 and tau2. So what we do here to get Q double dot as an isolated a vector here, Q double dot consists of Q1 double dot and Q2 double dot. So this D matrix that is multiplying here, so we need to transfer these terms on the other side as we did for other cases also, but now instead of dividing we take an inverse of D matrix here. So dq, this is a typically function of variables of the system, not dot variables not q dots here, only q. So this dq inverse multiplied with your transfer terms here, these are now forming a vector here. So that will give us q double dot, and once we obtain q double dot, our job is easy for us to kind of code this for the ODE solver. Okay, so you go through, like, you can solve such as examples also then very easily. So with these we can solve, n degree of freedom robotic manipulator equations and simulate them in MATLAB for whatever purposes, dynamics and control purposes that you want. Okay, so this is how, like, this leads you pathway for like multiple degree of freedom system simulation by using ODE 4.5 solver. There are like, some more issues that may come up regarding similarities, or some cases where your slopes are very high, okay, or your derivatives are becoming very high. Those cases we need to handle separately to make sure that there are some kind of other solvers called stiff solvers that can be used, or so these are like, that is a kind of a future pathway for us to get to. For now, you can like look at many different parameters that ODE function gives you to play around with and change to look at setting different settings of solving. Okay, so you can play around with that. That is all given in the MATLAB help. We will not get into that here, but that is a kind of a forward path to look for. Okay, so you can also see the demo of ODE 4.5 in MATLAB and like see play around with different things in the ODE function to get a good grasp of like what you want to do. Okay, so we have already seen the animation code, so we'll stop here for now, and you enjoy coding with this background, many different systems and assignments and things like that. For your future research also, this may be of quite immense help. Okay, so thank you and bye for now. We'll stop here.